Hey there, welcome to your Unit 8.1, 8.2 lesson. We're going to combine two lessons this time. So the first one is about expressing rates of reactions or reaction rates, same thing. Now, if you think about it, the word rate can also be replaced by speed. So that's really what we're doing here. We're trying to express the speed at which a reaction occurs. So what we need to look at is either the amount of reactants there is over time or the amount of products there is over time. So if I look here at my graph, if I, for example, start with the reactants, I would start with a certain amount of reactant at time 0. So let's say I start over here. Well, my reactants would slowly get depleted until there are no more left, at which point the reaction would stop. So if I were to take the variation of the amount of reactant over the variation of time, so delta y over delta x, I basically get the slope of my curve and also get the rate of my reaction based on the reactants. I could do the same thing with the products. So let's pretend we start, well, not let's pretend, but we will start at 0 for the products because at time 0 there are no products. So my products would increase until the reaction stops, which should be at the same point at which the reactants have totally disappeared, right? If there are no more reactants, there can't be any products produced. Now, if you think about it, because my products are being formed, this should have a positive slope or a positive rate. And for the reactants, my reactants would have a negative rate or a negative slope. Now, depending on the type of reaction I have, so let's pretend I have one reactant, AB, that gives me A plus 2B. I know this doesn't make sense, it's not quite balanced, but it's just for the sake of my example. That means that my substance A is produced half as fast as my substance B. For every A that I make 2 B's. So again, for every A that I make 2 molecules of B. So that means I'm making twice as much B as I am making substance A. How does this translate in terms of this graph? Oops, sorry. So that means my B should increase much more quickly, right? And I should have also more particles. So that's why my curve here is above, the green curve is above the red curve, because I have more B produced than I have A. But both being products, both curves will have a positive slope or a positive rate of reaction. So if I summarize a rate of reaction, what it is mathematically, it's a variation of quantity of substance over a variation of time. And like I said, for reactants, the rate is negative because they're being used up, and the products are positive, the rate is positive because they're being formed. So that's it for 8.1. Now let's take a look at 8.2. Obviously, we don't want to work for nothing. So when we can come up with a law or some kind of theory that we can apply to different situations, we try to do so. So here we're going to talk about the rate law, also called the general reaction rate. So the first comment I want to make is that those rate laws will always be proportional to the coefficients that we have. So I have 2 moles of the reactant that will form 4 moles of this product and 1 mole of this product. So here I've illustrated the molecules. So 2 molecules will react together to form 4 of this and 1 of this. So that means the rate should be proportional to that, the same way I showed you before, because I'm making 4 of these versus 1 of this. Well, I'm making the substance 4 times faster. So this is basically what is explained here. So this gets formed 4 times faster than this. I can also say that this is produced half as fast as this is being used. If I use 2 of these, but only produce 1 here, well, this is being used up twice as fast as this is being formed. Or I can say this is being formed half as quickly as this is being used up. Okay, so I can express it both ways. So bottom line, my rates respect these ratio, 2 for 4 for 1 in this particular case. Now mathematically, how do we play around with this? So we say, if I stick to the same equation, we're comparing in this case O2 and N2O5. So this one here and this one here. So we said because it's 2 for 1, well, that means this is produced half as quickly as this is, right? Because I use up 2 of these to make 1 of these. So this is produced half as quickly as this. And that's what's being expressed here. The rate of production of oxygen per unit of time is half of the rate of consumption of N2O5 per unit of time. And it's negative because it's being used up. So when we have a reactant, this over here will be negative. When we have a product, it'll be positive. So in the second example, we're comparing this substance with this substance. So knowing that I have a coefficient of 1 here, well, I can say this is produced 4 times as fast as this, or if I'm looking for the rate of oxygen, I'll say oxygen is produced 4 times more slowly than this one. So if it's 4 times more slowly, it's basically a quarter of the speed. That's what we have here. The rate of production of oxygen is a quarter, so 4 times slower than the rate of production of NO2. If you don't like this approach, just do a ratio. And I'll show you on the next page how this works. We can still work with ratio the same way we work with stoichiometry if you're not quite comfortable with this. So let me show you. Okay, so here we have the general reaction rate. So this here. So this here is equal to, these expressions are for each and every reactant and product in a given equation. So in this case, I have one reactant. So what I would put is the general reaction rate is equal to negative, because I'm talking about a reactant, 1 over the coefficient. In the case of N2O5, coefficient is 2, times the concentration of the substance, N2O5, over the variation of time. So here I have the variation of the concentration. That is also equal to, I'm going to skip this expression because I only have one reactant. I'll move on to this one, so the product side. Positive 1 over 4, because I'm looking at this one here, times the concentration of NO2, variation, over the variation of time. And that's equal to 1 over, in this case, my coefficient is 1, so 1 over 1, times the variation of concentration of O2 over the variation, of time. All right, so I can always go back and forth between my different substances. So my rates of reactions, my speeds of reaction, of production or depletion, basically always proportional to these ratios. So this is a very, I think, complicated way of expressing it. It works. If you're comfortable with it, fine. If you'd rather do standard ratios using these coefficients, that also works. What I mean is the following. If the speed is 5 mole per second of this is being used up, and I want to know how much of this is being produced at the same time, well, my ratio is 2 for 1. It's 5 for x. So I basically have, I only need to cross multiply. 5 times 1 divided by 2 will give me 2.5. So it would be 2.5 mole of O2 would be produced per second. By doing this, you're essentially doing the same thing as you're doing here, but it's just much faster and much simpler. But again, if you want to use this approach, there's no problem with it. You should be somewhat comfortable with it in case you're asked to actually use it if it's mandatory to use it. So you have to kind of understand it, but given a choice, you can either use this approach or this approach. That's fine. So here's just more of the same. Rather than saying, if I just go back for a second, rather than saying concentration over time, because a quantity over time is the same thing as saying a rate, they've just replaced R, or they've just replaced concentration over time, I should say, by the letter R. So up there, they were showing concentration over time. Here, they're keeping the same fractions, but they're replacing concentration over time by the word rate, which is one and the same. So here comes your example. Ammonia, NH3. So we're going to be talking about this one here. Is used in agriculture as a chemical fertilizer. It is produced by the reaction of nitrogen with hydrogen as shown in the equation. Okay, the rate of ammonia production, so ammonia production over here, is 5.0 times 10 to the negative 6 mole per liter second. Okay, what is the general reaction rate? Well, we said, and you see in this case, it's kind of mandatory that you use that law I just showed you. The general reaction rate is equal to 1 over the coefficient, in this case 2, times the rate of NH3. Because we're talking about a product, this is positive. So the only thing I need to do if I want to find the general reaction rate is replace this over here, the R, by this value, because that's the rate that's given to me. So essentially I'm doing this divided by 2. So that's what they're getting here. 5 divided by 2 is 2.5, which is what you're getting here. 2.5 times 10 to the negative 6 mole per liter second. Now in B, what are the corresponding rates of nitrogen and hydrogen? Again, you can use this format, which I showed you before. So 1 over the coefficient. Coefficient over here is 1. So 1 over 1 times the rate of N2 is equal to 1 over 3 times the rate of H2 is equal to 1 over 2 times the rate of NH3. One thing you may notice here is that you don't have any positives and negatives. When you have just the rate, they use the absolute value. When you have actual concentration over time, then you put the positive and the negative. So that's a distinction you have to remember. If it's just the rate, as silly as it may sound, if you just have the rate, it's absolute value, it's positive, no matter what. If you're doing concentration over time, then you have to put the positive and the negative depending on if you're talking about a reactant or a product. So back to this. What are the rates for nitrogen and hydrogen? So like I said, you can use this, or you can just cross multiply and say, well, if this is 5 times 10 to the negative 6, let me find the rate here and the rate here by cross multiplying. So this times 3 divided by 2 will give me the rate of hydrogen. This times 1 divided by 2 will give me the rate of nitrogen, which is the case here. So I have my answer here. 5 times 1 divided by 2, so 5 divided by 2 is 2.5. There you go. And 5 times 3, which is 15, divided by 2 gives me 7.5, which is what we get over here. So again, it all comes down to what you're more comfortable with. Would you rather use this type of equation, or would you rather just cross multiply? It's really up to you. Finally, hydrogen cyanide. HCN is a highly toxic gas produced from methane, ammonia, blah, blah, blah. Okay, what is the rate of hydrogen, so this here, formation, if the concentration of ammonia goes from 0.2 to 0.06 in 90 seconds? So now they're forcing you to use concentration over time, and that is why they use signs over here, positive and negative. So negative and negative for the reactants, positive, positive for the products. So they do 1 over the coefficient times the concentration of the substance over variation of time, etc., etc. Now, they want to know what will be this rate, but they give you ammonia. So they give you this one here. So what we're interested in is this one versus this one. So you can again replace, or you can do it the faster way and say, okay, let's calculate first of all the rate for ammonia. So it goes from 0.2 to 0.06. If we do final minus initial over the change of time, we get the rate of ammonia. So ammonia has a rate of 1.6 times 10 to the negative 3 mole per liter second. And here you see why they put a negative in the front. They put a negative to offset the fact that your change of concentration would be negative, which doesn't, well, it's not that it doesn't make sense. You know it's disappearing, but ultimately you don't want a negative answer because it doesn't really make sense. You can't have a negative amount of moles unless you're really trying to express the fact that it's disappearing, which is the case here. But all that to say that they put the negative to offset the fact that this will give you a negative delta concentration. So the rate of an H3 is this here. So what I can do is replace here and solve for this here, or what I prefer is again to cross multiply. So it's 1 NH3 for 3 H2. So that means it's going to be 1.6 times 10 to the negative 3 for how much? Well, this times 3 divided by 1 is equal to the rate I'm looking for. So basically this times 3, which gives me 4.8 times 10 to the negative 3 mole per liter second. There you go. That's 8.1, 8.2. See you for 8.3.